the corresponding components and then adding the results, which is good since so much of our computation has to look like weighted sums. Geometrically, the dot product is positive when vectors point in similar directions, it's 0 if they're perpendicular, and it's negative whenever they point in opposite directions. For example, let's say you were playing with this model and you hypothesize that the embedding of cats minus cat might represent a sort of plurality direction in this space. To test this, I'm going to take this vector and compute its dot product against the embeddings of certain singular nouns and compare it to the dot products with the corresponding plural nouns. If you play around with this, you'll notice that the plural ones do indeed seem to consistently give higher values than the singular ones, indicating that they align more with this direction. It's also fun how if you take this dot product with the embeddings of the words 1, 2, 3, and so on, they give increasing values, so it's as if we can quantitatively measure how plural the model finds a given word. Again, the specifics for how words get embedded is learned using data. This embedding matrix, whose columns tell us what happens to each word, is the first pile of weights in our model, and using the GPT-3 numbers, the vocabulary size specifically is 50,257, and again, technically this consists not of words per se, but of tokens. And the embedding dimension is 12,288. Multiplying those tells us this consists of about 617 million weights. Let's go ahead and add this to a running tally, remembering that by the end, we should count up to 175 billion. In the case of transformers, you really want to think of the vectors in this embedding space as not merely representing individual words. For one thing, they also encode information about the position of that word, which we'll talk about later. But more importantly, you should think of them as having the capacity to soak in context. A vector that started its life as the embedding of the word king, for example, might progressively get tugged and pulled by various blocks in this network, so that by the end it points in a much more specific and nuanced direction that somehow encodes that it was a king who lived in Scotland, and who had achieved his post after murdering the previous king, and who's being described in Shakespearean language. Think about your own understanding of a given word. The meaning of that word is clearly informed by the surroundings, and sometimes this includes context from a long distance away. So in putting together a model that has the ability to predict what word comes next, the goal is to somehow empower it to incorporate context efficiently. To be clear, in that very first step, when you create the array of vectors based on the input text, each one of those is simply plucked out of the embedding matrix. So initially, each one can only encode the meaning of a single word without any input from its surroundings. But you should think of the primary goal of this network that it flows through as being to enable each one of those vectors to soak up a meaning that's much more rich and specific than what mere individual words could represent. The network can only process a fixed number of vectors at a time, known as its context size. For GPT-3, it was trained with a context size of 2048, so the data flowing through the network always looks like this array of 2048 columns, each of which has 12,000 dimensions. This context size limits how much text the transformer can incorporate when it's making a prediction of the next word. This is why long conversations with certain chatbots, like the early versions of ChatGPT, often gave the feeling of the bot kind of losing the thread of conversation as you continued too long. We'll go into the details of attention in due time, but skipping ahead, I want to talk for a minute about what happens at the very end. Remember, the desired output is a probability distribution over all tokens that might come next. For example, if the very last word is professor, and the context includes words like Harry Potter, and immediately preceding we see least favorite teacher, and also if you give me some leeway by letting me pretend that tokens simply look like full words, then a well-trained network that had built up knowledge of Harry Potter would presumably assign a high number to the word Snape. This involves two different steps. The first one is to use another matrix that maps the very last vector in that context to a list of 50,000 values, one for each token in the vocabulary. Then there's a function that normalizes this into a probability distribution. It's called softmax, and we'll talk more about it in just a second. But before that, it might seem a little bit weird to only use this last embedding to make a prediction, when after all, in that last step, there are thousands of other vectors in the layer just sitting there with their own context-rich meanings. This has to do with the fact that in the training process, it turns out to be much more efficient if you use each one of those vectors in the final layer to simultaneously make a prediction for what would come immediately after it. There's a lot more to be said about training later on, but I just want to call that out right now. This matrix is called the unembedding matrix, and we give it the label WU. Again, like all the weight matrices we see, its entries begin at random, but they are learned during the training process. Keeping score on our total parameter count, this unembedding matrix has one row for each word in the vocabulary, and each row has the same number of elements as the embedding dimension. It's very similar to the embedding matrix, just with the order swapped, so it adds another 617 million parameters to the network, meaning our count so far is a little over 1 billion. A small, but not wholly insignificant fraction of the 175 billion that we'll end up with in total. As the very last mini-lesson for this chapter, I want to talk more about the softmax function, since it makes another appearance for us once we dive into the attention blocks. The idea is that if you want a sequence of numbers to act as a probability distribution, say a distribution over all possible next words, then each value has to be between 0 and 1, and you also need all of them to add up to 1. However, if you're playing the deep learning game, where everything you do looks like matrix vector multiplication, the outputs that you get by default don't abide by this at all. The values are often negative or much bigger than 1, and they almost certainly don't add up to 1. Softmax is the standard way to turn an arbitrary list of numbers into a valid distribution in such a way that the largest values end up closest to 1, and the smaller values end up very close to 0. That's all you really need to know. But if you're curious, the way that it works is to first raise e to the power of each of the numbers, which means you now have a list of positive values, and then you can take the sum of all those positive values and divide each term by that sum, which normalizes it into a list that adds up to 1. You'll notice that if one of the numbers in the input is meaningfully bigger than the rest, then in the output, the corresponding term dominates the distribution. So if you were sampling from it, you'd almost certainly just be picking the maximizing input. But it's softer than just picking the max, in the sense that when other values are similarly large, they also get meaningful weight in the distribution, and everything changes continuously as you continuously vary the inputs. In some situations, like when ChatGPT is using this distribution to create a next word, there's room for a little bit of extra fun by adding a little extra spice into this function with a constant t thrown into the denominator of those exponents. We call it the temperature, since it vaguely resembles the role of temperature in certain thermodynamics equations, and the effect is that when t is larger, you give more weight to the lower values, meaning the distribution is a little bit more uniform, and if t is smaller, then the bigger values will dominate more aggressively. Where in the extreme, setting t equal to 0 means all of the weight goes to that maximum value. For example, I'll have GPT-3 generate a story with the seed text, "Once upon a time there was a," but I'm going to use different temperatures in each case. Temperature 0 means that it always goes with the most predictable word. And what you get ends up being kind of a trite derivative of Goldilocks. A higher temperature gives it a chance to choose less likely words, but it comes with a risk. In this case, the story starts out a bit more originally, about a young web artist from South Korea, but it quickly degenerates into nonsense. Technically speaking, the API doesn't actually let you pick a temperature bigger than 2. There is no mathematical reason for this. It's just an arbitrary constraint imposed, I suppose, to keep their tool from being seen generating things that are too nonsensical. So if you're curious, the way this animation is actually working is I'm taking the 20 most probable next tokens that GPT-3 generates, which seems to be the maximum they'll give me, and then I tweak the probabilities based on an exponent of 1/5. As another bit of jargon, in the same way that you might call the components of the output of this function probabilities, people often refer to the inputs as logits, or some people say logits, some people say logits. I'm going to say logits. So for instance, when you feed in some text, you have all these word embeddings flow through the network, and you do this final multiplication with the unembedding matrix. Machine learning people would refer to the components in that raw, unnormalized output as the logits for the next word prediction. A lot of the goal with this chapter was to lay the foundations for understanding the attention mechanism, Karate Kid wax on, wax off style. You see, if you have a strong intuition for word embeddings, for softmax, for how dot products measure similarity, and also the underlying premise that most of the calculations have to look like matrix multiplication with matrices full of tunable parameters, then understanding the attention mechanism, this cornerstone piece in the whole modern boom in AI, should be relatively smooth. For that, come join me in the next chapter. As I'm publishing this, a draft of that next chapter is available for review by Patreon supporters. A final version should be up and public in a week or two. It usually depends on how much I end up changing based on that review. In the meantime, if you want to dive into attention, and if you want to help the channel out a little bit, it's there waiting. In the last chapter, you and I started to step through the internal workings of a transformer. This is one of the key pieces of technology inside large language models and a lot of other tools in the modern wave of AI. It first hit the scene in a now famous 2017 paper called Attention is All You Need, and in this chapter, you and I will dig into what this attention mechanism is, visualizing how it processes data. As a quick recap, here's the important context I want you to have in mind. The goal of the model that you and I are studying is to take in a piece of text and predict what word comes next. The input text is broken up into little pieces that we call tokens, and these are very often words or pieces of words. But just to make the examples in this video easier for you and me to think about, let's simplify by pretending that tokens are always just words. The first step in a transformer is to associate each token with a high-dimensional vector, what we call its embedding. Now, the most important idea I want you to have in mind is how directions in this high-dimensional space of all possible embeddings can correspond with semantic meaning. In the last chapter, we saw an example for how direction can correspond to gender, in the sense that adding a certain step in this space can take you from the embedding of a masculine noun to the embedding of the corresponding feminine noun. That's just one example. You could imagine how many other directions in this high-dimensional space could correspond to numerous other aspects of a word's meaning. The aim of a transformer is to progressively adjust these embeddings so that they don't merely encode an individual word, but instead they bake in some much richer contextual meaning. I should say up front that a lot of people find the attention mechanism, this key piece in a transformer, very confusing, so don't worry if it takes some time for things to sink in. I think that before we dive into the computational details and all the matrix multiplications, it's worth thinking about a couple examples for the kind of behavior that we want attention to enable. Consider the phrases American true mole, 1 mole of carbon dioxide, and take a biopsy of the mole. You and I know that the word mole has different meanings in each one of these, based on the context. But after the first step of a transformer, the one that breaks up the text and associates each token with a vector, the vector that's associated with mole would be the same in all three of these cases, because this initial token embedding is effectively a lookup table with no reference to the context. It's only in the next step of the transformer that the surrounding embeddings have the chance to pass information into this one. The picture you might have in mind is that there are multiple distinct directions in this embedding space, encoding the multiple distinct meanings of the word mole, and that a well-trained attention block calculates what you need to add to the generic embedding to move it to one of these more specific directions, as a function of the context. To take another example, consider the embedding of the word tower. This is presumably some very generic, non-specific direction in the space, associated with lots of other large, tall nouns. If this word was immediately preceded by Eiffel, you could imagine wanting the mechanism to update this vector so that it points in a direction that more specifically encodes the Eiffel Tower, maybe correlated with vectors associated with Paris and France and things made of steel. If it was also preceded by the word miniature, then the vector should be updated even further so that it no longer correlates with large, tall things. More generally than just refining the meaning of a word, the attention block allows the model to move information encoded in one embedding to that of another, potentially ones that are quite far away, and potentially with information that's much richer than just a single word. What we saw in the last chapter was how after all of the vectors flow through the network, including many different attention blocks, the computation that you perform to produce a prediction of the next token is entirely a function of the last vector in the sequence. So imagine, for example, that the text you input is most of an entire mystery novel, all the way up to a point near the end, which reads, "Therefore the murderer was." If the model's going to accurately predict the next word, that final vector in the sequence, which began its life simply embedding the word was, will have to have been updated by all of the attention blocks to represent much more than any individual word, somehow encoding all of the information from the full context window that's relevant to predicting the next word. To step through the computations, though, let's take a much simpler example. Imagine that the input includes the phrase, "A fluffy blue creature roamed the verdant forest." And for the moment, suppose that the only type of update that we care about is having the adjectives adjust the meanings of their corresponding nouns. What I'm about to describe is what we would call a single head of attention, and later we will see how the attention block consists of many different heads run in parallel. Again, the initial embedding for each word is some high-dimensional vector that only encodes the meaning of that particular word with no context. Actually, that's not quite true. They also encode the position of the word. There's a lot more to say about the specific way that positions are encoded, but right now, all you need to know is that the entries of this vector are enough to tell you both what the word is and where it exists in the context. Let's go ahead and denote these embeddings with the letter E. The goal is to have a series of computations produce a new refined set of embeddings where, for example, those corresponding to the nouns have ingested the meaning from their corresponding adjectives. And playing the deep learning game, we want most of the computations involved to look like matrix vector products, where the matrices are full of tunable weights, things that the model will learn based on data. To be clear, I'm making up this example of adjectives updating nouns just to illustrate the type of behavior that you could imagine an attention head doing. As with so much deep learning, the true behavior is much harder to parse, because it's based on tweaking and tuning a huge number of parameters to minimize some cost function. It's just that as we step through all of the different matrices filled with parameters that are involved in this process, I think it's really helpful to have an imagined example of something that it could be doing to help keep it all more concrete. For the first step of this process, you might imagine each noun, like creature, asking the question, "Hey, are there any adjectives sitting in front of me?" And for the words fluffy and blue to each be able to answer, "Yeah, I'm an adjective and I'm in that position." That question is somehow encoded as yet another vector, another list of numbers, which we call the query for this word. This query vector, though, has a much smaller dimension than the embedding vector, say 128. Computing this query looks like taking a certain matrix, which I'll label WQ, and multiplying it by the embedding. Compressing things a bit, let's write that query vector as Q, and then anytime you see me put a matrix next to an arrow like this one, it's meant to represent that multiplying this matrix by the vector at the arrow's start gives you the vector at the arrow's end. In this case, you multiply this matrix by all of the embeddings in the context, producing one query vector for each token. The entries of this matrix are parameters of the model, which means the true behavior is learned from data, and in practice, what this matrix does in a particular attention head is challenging to parse. But for our sake, imagining an example that we might hope that it would learn, we'll suppose that this query matrix maps the embeddings of nouns to certain directions in this smaller query space that somehow encodes the notion of looking for adjectives in preceding positions. As to what it does to other embeddings, who knows? Maybe it simultaneously tries to accomplish some other goal with those. Right now, we're laser focused on the nouns. At the same time, associated with this is a second matrix called the key matrix, which you also multiply by every one of the embeddings. This produces a second sequence of vectors that we call the keys. Conceptually, you want to think of the keys as potentially answering the queries. This key matrix is also full of tunable parameters, and just like the query matrix, it maps the embedding vectors to that same smaller dimensional space. You think of the keys as matching the queries whenever they closely align with each other. In our example, you would imagine that the key matrix maps the adjectives, like fluffy and blue, to vectors that are closely aligned with the query produced by the word creature. To measure how well each key matches each query, you compute a dot product between each possible key-query pair. I like to visualize a grid full of a bunch of dots, where the bigger dots correspond to the larger dot products, the places where the keys and queries align. For our adjective-noun example, that would look a little more like this, where if the keys produced by fluffy and blue really do align closely with the query produced by creature, then the dot products in these two spots would be some large positive numbers. In the lingo, machine learning people would say that this means the embeddings of fluffy and blue attend to the embedding of creature. By contrast to the dot product between the key for some other word, like the, and the query for creature, would be some small or negative value that reflects that these are unrelated to each other. So we have this grid of values, that can be any real number from -infinity to infinity, giving us a score for how relevant each word is to updating the meaning of every other word. The way we're about to use these scores is to take a certain weighted sum along each column, weighted by the relevance. So instead of having values range from -infinity to infinity, what we want is for the numbers in these columns to be between 0 and 1, and for each column to add up to 1, as if they were a probability distribution. If you're coming in from the last chapter, you know what we need to do then. We compute a softmax along each one of these columns to normalize the values. In our picture, after you apply softmax to all of the columns, we'll fill in the grid with these normalized values. At this point, you're safe to think about each column as giving weights according to how relevant the word on the left is to the corresponding value at the top. We call this grid an attention pattern. Now, if you look at the original Transformer paper, there's a really compact way that they write this all down. Here, the variables q and k represent the full arrays of query and key vectors respectively, those little vectors you get by multiplying the embeddings by the query and the key matrices. This expression up in the numerator is a really compact way to represent the grid of all possible dot products between pairs of keys and queries. A small technical detail that I didn't mention is that for numerical stability, it happens to be helpful to divide all of these values by the square root of the dimension in that key query space. Then this softmax that's wrapped around the full expression is meant to be understood to apply column by column. As to that v term, we'll talk about it in just a second. Before that, there's one other technical detail that so far I've skipped. During the training process, when you run this model on a given text example, and all of the weights are slightly adjusted and tuned to either reward or punish it based on how high a probability it assigns to the true next word in the passage, it turns out to make the whole training process a lot more efficient if you simultaneously have it predict every possible next token following each initial subsequence of tokens in this passage. For example, with the phrase that we've been focusing on, it might also be predicting what words follow creature and what words follow the. This is really nice because it means what would otherwise be a single training example effectively acts as many. For the purposes of our attention pattern, it means that you never want to allow later words to influence earlier words, since otherwise they could kind of give away the answer for what comes next. What this means is that we want all of these spots here, the ones representing later tokens influencing earlier ones, to somehow be forced to be 0. The simplest thing you might think to do is to set them equal to 0, but if you did that, the columns wouldn't add up to 1 anymore. They wouldn't be normalized. So instead, a common way to do this is that before applying softmax, you set all of those entries to be -infinity. If you do that, then after applying softmax, all of those get turned into 0, but the columns stay normalized. This process is called masking. There are versions of attention where you don't apply it, but in our GPT example, even though this is more relevant during the training phase than it would be, say, running it as a chatbot or something like that, you do always apply this masking to prevent later tokens from influencing earlier ones. Another fact that's worth reflecting on about this attention pattern is how its size is equal to the square of the context size. So this is why context size can be a really huge bottleneck for large language models, and scaling it up is non-trivial. As you might imagine, motivated by a desire for bigger and bigger context windows, recent years have seen some variations to the attention mechanism aimed at making context more scalable. But right here, you and I are staying focused on the basics. Okay, great. Computing this pattern lets the model deduce which words are relevant to which other words.